Okay, so now I am going to share the screen. Okay. Okay, so I hope all of you can see the screen now. Okay, so I was explaining this diagram that this diagram you can see in IS 456 also. So this is our strain diagram, which is exactly same with the working stress. That means your at the neutral axis your strain is 0. Above the neutral axis these are our compressive strain, and above the below the neutral axis these are our tensile strain. Okay. So according to IS 456, the maximum strain in concrete it is 0.0035. You can see here, this is the maximum strain, 0.0035. Okay, and you see the diagram here, 0.002. So beyond this point, your strain will be linear, but your strain, you can see your strain will be gradually increasing, but you can see your stress is constant. This diagram is coming from this stress strain behavior. Okay, so at this point you can see after reaching 0.002, that means this is our strain, along the x-axis you can see the strain is increasing, but beyond this point you can see the stress at this point. Wait, I will show you. At this point our strain is 0.002. Okay, so initially at the this is our neutral axis. Okay, this is our neutral axis in the origin, that means our neutral axis. Your stress is 0, strain is 0. Okay, so as we go on increasing the load, our stress strain graph is parabolic up to this point. So at this point you can see our strain is 0.002. so beyond this point you can see at this point what is the stress. Our stress is here. Okay, this is the value of stress, 0.446 times of FCK. Okay, so beyond this point you can see the stress is constant. Stress is constant, and but the strain is continuously increasing. First it was 0.002 and finally it will reach 0.0035. Okay, so after reaching this point your concrete will fail. Okay, so here in this diagram you can see this is the strain diagram. So at this point it is 0.002. so corresponding to this point, if you see here up to this point you can see this is our parabolic portion. Okay, so beyond this point you can see our stress is constant, same stress is constant, straight line, that means it is constant, but you can see our strain is continuously increasing. Okay, so after reaching this point, that means after reaching this value 0.0035, which is called your ultimate strain, our concrete will fail. Okay, so this much is the value of maximum or ultimate strain, 0.0035, and at this point corresponding to this.
Hello, sir.
Yes.
So your voice is low.
Voice is low.
Yes.
But my sound is to maximum sound here. You check use your earphone. Okay, so what about the other students? My voice is audible or is it very low? Audible. Okay. Okay, so and those who are getting low voice, you try your earphone. Okay, because I am putting my maximum sound here. Okay, so this is 100. So I can't increase the sound anymore. Okay, so you try your earphone also once. Okay, to.
Okay, sir. Okay, sir.
Okay. So this graph is our strain diagram and this is our stress diagram, and both the diagrams are coming from this stress strain behavior of concrete. Okay, this is our stress, this is our strain. From this point is our neutral axis. So from the neutral axis our stress and strain behavior is parabolic. So as soon as our strain becomes 0.002, And from that point, our stress will become constant, and that value is your 0.446 FCK, or you can say 0.45 FCK. Okay. So after reaching this value 0.0035, our concrete will fail. That means this is our ultimate point, this line. After reaching this strain, our concrete will fail. Okay. So this value is shown in this stress strain behavior, this value. Okay, so this is our stress 0.446, this is our strain. And okay, so now this is our compression portion. That means above the neutral axis we have concrete in this portion. So this is our compression zone. Below the neutral axis, this is our tension zone. Okay, so I have told you before also why there is nothing here, because the tensile strength of concrete is ignored. According to the assumption also, it is written here, the tensile strength of concrete is ignored. That means you can see here, according, these are the assumptions. The tensile strength of concrete is ignored. That means the whole tensile stress will be taken up by steel. Okay, that's why in this diagram, in this diagram you can see there is nothing in this portion, because in this portion we have concrete. So since the strength of concrete is ignored, that means concrete is not taking any tensile stresses, and the entire tensile stress will be taken up by this amount, this steel. Okay, and the value of tensile stress is, our design strength is this much, and area of steel is AST. So stress into area, we will get tensile force. Okay, because force equal to stress into area. So our stress is 0.87 Fy, area is area is AST. So if you multiply these two values, we will get the total tensile force. So similarly here, for getting the compressive force, we have to do the same. Okay, this okay, so can you tell me what will be the value of total compressive force here? Total compressive force. Total compressive force. We have to multiply the stress by the area of this portion, is it? Total compressive force will be stress, compressive stress into the area of this section. Okay, so now I will show you how to find out this Cu. Okay, and it is also directly written in IS code. Cu equal to, the value is given. Okay, so here you see, this is the explanation of this maximum ultimate strain. This is 0. Okay. Okay, stress block parameter. According to IS 456, area of stress block, this area of stress block is 0.36 FCK B into XU. This value is given in IS 456. This value is given. You can see the in the assumptions. Clause number 38, page number 68 or 69. You see the values, you will get this. Can you see this value, all of you, in the IS code? This value? All of you, can you see the value in IS 456? No, sir. Okay, wait, I will open the IS 456. See this value, area of stress block. This value is given. Area of stress block, you can see this value. Okay, here you have to do one correction. This value is 0.36 FCK B into XU. B is not mentioned by mistakenly, it is not printed. You have to do the correction. This value will be 0.36 FCK B into XU. B value is missing here. This B is missing in IS code. All of you, please do the correction. Area of stress block will be 0.36 FCK B into XU. B into XU. Okay, and the total compressive force will act at a distance of 0.4 times of XU. Okay, so what is this XU? XU means in the previous working stress method, we represent the depth of neutral axis by NA or NC. Okay, but here in this limit state method, we will represent the depth of neutral axis by XU. You can see here, this is our neutral axis. So the depth of neutral axis we will represent it by XU in limit state method. So in the previous working stress method, we represented the value by NC and N. Okay, but here we will represent it by XU. Okay. Okay, so total compressive force will be this much, and the total depth of this total compressive force from the topmost fiber is 0.42 XU. This is also written in IS 456. You can see here, depth of center of compressive force, it is 0.42 XU. Okay, here it is written XU means depth of neutral axis, and FCK, you know, all of you know that, characteristic compressive strength of concrete. Okay, okay, so okay, so all of you have got this. Okay, so let us move to the next part. So next, how to find out this depth of neutral axis. So our aim will be to find out the depth of neutral axis. So now in this limit state method, the formula will be different, and the formula is directly given in IS 456. No need to remember that also. Okay, so all of you must remember this diagram. The strain diagram is maximum strain is 0.0035, and the maximum strain in steel is this much. I have shown you in the diagram of stress strain behavior of steel. Okay, this value is mentioned in that stress strain behavior of steel. Okay, so maximum stress in steel is 0.87 FY/AST, and the total tensile forces is this much, and total compressive forces this much. These are given as 456. Okay, so now previously what we have done to find out the neutral axis, we have to multiply this, we have to equate these two values. Total compression equal to total tension. C equal to T. This equal to this. Okay. So if you equate these two values, we can find out the value of XU. That means our depth of neutral axis. Okay. Total tension is this much. Total compression is this much. So for equilibrium, we have to, our total tension must be equal to total compression. So if you see these two values, X is equal to this much. Okay, and you don't need to remember these values, but okay, because this value is already mentioned in IS 456. Okay, so all of you please go to the clause number G.1.1 of IS 456. It will be the almost last page of IS 456. You go to that page, last page of IS 456. Yeah, this page number 96. Go to page number 96. Go to page number 96, annexure G. Annexure G, moment of resistance for rectangular anti-sections. All of you got this? All of you got this clause? Okay. So in this clause you can see here for rectangular section, because we are dealing with rectangular section at present. So the depth of neutral axis we can find out by using this formula. And this is nothing but the formula I am showing you. This one. Actual value is this one, but if you divide this XU by D, you have to divide this side also by D. So XU by D equal to this much. So no need to remember that because you have IS 456 with you. So directly you can use IS 456. Okay, so we can use this formula to find out the depth of neutral axis. Okay, XU, and this XU is your actual neutral axis, actual depth of neutral axis. Okay, this XU equal to depth of actual neutral axis. Okay, so next, okay, so now you see limiting depth of neutral axis. That means the maximum value of depth of neutral axis. So you can see it is written here, the strain distribution for single reinforced beam is this much, it is written. So for finding out the maximum value of the depth of neutral axis, XU max, or in IS 456 it is written by MU XU lim. No, it is written XU max only. Okay. So for getting the maximum value of neutral axis, we have to use this formula. All of you must remember this formula to find out the value of maximum depth of neutral axis. This is the formula to find out limiting value or maximum value of depth of neutral axis. This formula all of you must remember because this formula is not given in IS 456. This formula is not given in IS 456, so all of you must remember this formula. D value will be given, Fy value will be given, Es is the modulus of elasticity of steel. Okay. So if you know these values, you can find out the value of the maximum value of neutral axis. Okay. So now you must know what is this XU max. XU max means maximum value. But why we need to find out maximum value and what is the use of it? What is the significance of this? This value of, what is the significance of this XU max? We must know that. Okay. So in previous method, that means our in working stress method, we compared the values of actual neutral axis and critical neutral axis. But now in limit state method, we don't have critical neutral axis. We have the value of this one, XU max, maximum value of neutral axis. Okay. So we have to compare the value of XU and XU max. And based on that two values, we can say whether this is a balanced section or over reinforced section or under reinforced section. Okay. So can anyone guess what is the what do you mean by XU max, maximum value of neutral axis or limiting value of neutral axis? Anyone? Anyone have any idea what is the meaning of maximum or limiting depth of neutral axis? No, sir. Anyone have any idea? You can guess also. You can guess the value. Okay, so limiting value of what? Limiting value of, okay, so it is, the name itself says it is the maximum value of neutral axis. Maximum value of neutral axis, which is limited to ensure that we will get an under reinforced section. Okay, so the limiting value or maximum value of depth of neutral axis means the maximum depth of neutral axis which is limited to ensure that the tensile steel will reach the permissible stress before the concrete fails. Okay, so it is the maximum depth of neutral axis, means it is the maximum depth which we can allow to get an under reinforced section. Just simple meaning is that it is the maximum depth of neutral axis which is limited to ensure that the tensile steel will reach the permissible stress before the concrete fails, or we can say that the maximum depth which we can allow to get an under reinforced section, because under reinforced section is always preferred over reinforced section. I have already told you before what is the reason behind that. Okay, so we have to find XU as well as we have to find out XU max. I hope all of you can see the chat box. UR means under reinforced. Okay, UR means under reinforced. Okay, so XU max means the maximum depth of neutral axis which we can allow to get an under reinforced section. The simple meaning is that. Simple meaning is that. Okay. So by using this formula, we can find out that depth, how much we can allow to get an under reinforced section. Okay. So in IS 456, the ratio of XU max by D is given. Okay. So all of you go to clause number. I forgot the exact clause number, but all of you please remember the clause. Okay. If you don't remember, you write down in your copies. What are the clause numbers we will use throughout the syllabus? Clause number 38 we have to use throughout the syllabus. Then this annexure G point 1.1 we have to use throughout the semester. Then now I will show you XU max by D. Yeah, it is in clause number 38 only. Clause number, I think page number 70, just below the stress strain diagram, you see this table. See, all of you please go through the table. So the limiting values of depth of neutral axis for different grades of steel are given in IS 456. All of you got this table, all of you? Page number 70, clause number 38. Can you see the table, all of you? Okay, okay. I hope all of you have got the table. Okay, so now in this table you can see, all of you, you can see that for different grades of steel, we have the ratio of maximum depth of neutral axis by, this is our effective depth. Okay, the limiting values of depth for neutral axis for different grades of steel are given. Okay, so if in your question Fe415 is given, and if the depth of neutral, if your effective depth is given, we can directly find out what is the value of XU max. Okay, that means maximum depth of neutral axis. So XU max will be, for Fe415 it will be 0.48D, for Fe250 it will be 0.53D, and for this one Fe500 it will be 0.46D. Okay, but for using this table we have to remember this clause. Okay, clause number 38. This clause, I am telling you again and again, this clause number is very important. This clause number 38. Throughout the semester, we have to use this clause. So all of you, please remember this clause number 38. Almost for every problem, we have to use this clause number. Okay, so we have got the values of this axiom x by d. Next, our aim will be to find out the moment of resistance. Okay, so here also to find out the moment of resistance, no need to remember the value. I told you before that the moment of resistance is nothing but the moment of resistance is what? The maximum moment which the beam can resist. But in this figure, how can we find out? The moment is nothing but total compressive force into lever arm or total tensile force into lever arm. Lever arm means the distance between the total compressive force and the total tensile force. Okay, so total compressive force is at a distance of 0.42 XU as according to IS 456. This total depth is our D, effective depth, this is our D. So this lever arm will be written by A equal to D minus this distance, D minus 0.42 XU. You can see here. So to get the moment of resistance, we can use two formulas, C into A or T into A. So C means this value into A means this one, or T into A. T means total tensile force equal to this value into A means this value. Okay, you can see here moment of resistance equal to C into lever arm or T into lever arm. Okay, so C means this value into lever arm, you multiply this is our lever arm. Okay, so if you put these two values, if you take D common, from here, it will be B into D, you will get this formula. Moment of resistance formula, you will get this one. Okay, you will get this formula. Okay, so again, you don't need to remember this formula because this formula is also given in IS 456. We don't need to remember any formula in case of limit state method. Again, all of you, please go to your annexure G. All of you go to annexure G. Page number 96. Yeah, 96. All of you go to annexure 96. Annexure G. Page number 96. Page number 96, annexure G. You can see here the formula moment of resistance is written here, this formula. Hello? Can you hear my voice, all of you? Hello? Okay. So moment of resistance you can find out by this formula. 0.36 FCK XU by D. This formula you can use to find out moment of resistance. Okay. Similarly, if you use T into lever arm, we are getting this value. Okay. This is our stress into lever arm. If you take D common, then finally you will get this. Okay, which is given in IS 456. This formula 0.87 FY ASTD. This formula. Okay. So next, again another term we have got, which is our limiting value of moment of resistance. Okay, limiting means in place of XU you have to place XU max. In place of this XU you have to write down XU max. So according to this formula, you are getting formula is 0.36 FCK. Now it will become XU max. Here it will become axiom x. This one. Okay. For limiting means maximum value of moment of resistance. So in place of XU, you have to put just XU max. Okay. So now for different grades of steel, we have this value of XU max by D. I have shown you the values for Fe415, Fe250 and 500. So for different grades of steel, we can find out this, we can modify this formula. Okay. Mu lim, we can modify it. For Fe250, XU max by D is 0.53. So if you put these values here, XU max by D is equal to 0.53, XU max by D is equal to 0.53, then the formula will become this one, 0.148 FCK BD square. Okay. Similarly, for you can see here, different grades of concrete are given. Mild steel for Fe415, for Fe500. All values are given. Mu equal to for M15, you will get this formula. For M20, this. For M25, for this. Okay. If you put, now you have got this formula. For M15, put the value of FCK equal to 15. For M20, put the value of FCK, you will get this formula. For M25, this is 25. For M30, this is 30. For M35, this is 35. So if you put all the values here, this is the actual formula for Fe250, that means for mild steel. But for different grades of concrete, you just need to put the values of FCK and you will get this one. No need to remember these things. Only you need to remember this one. For Fe250, the limiting value or the maximum value of moment of resistance is this one, 0.148 FCK BD square. Similarly, for Fe415, mu lim will become this one. And for Fe500, mu lim equal to this much. Okay. For different grades of concrete, you can directly find out the values. No need to remember anything. Only you have to remember these three values. Okay. Next, percentage of steel. Similarly, percentage of steel also we can find out from IS 456. Same procedure. We have to equate the total tensile force equal to total compressive force. So AST by BD will give you the total percentage of steel. Okay. Percentage of steel will formula will become this one. Okay. For Fe250, we can find out the value. Percentage of steel AST by BD equal to, this is the formula to find out percentage of steel. And I think this formula is also given in IS 456. No, it is not given. This is the formula to find out percentage of steel. Okay, so we will discuss this balanced under reinforced and over reinforced sections in the next class. Okay, and I will share the PDF with you. No need to worry for that. Okay, at the end of the class, not today. Okay, so I will share at the end of today's class. Okay, I will share the PDF with you. At the end of today's class, I will share the PDF in your group, or I can share the PDF with Shirodha. Okay, so all of you go through the PDF, and if you don't understand anything, if you have any doubt in any formula, you can ask me in the next class. Okay, and this part, this over reinforced, under reinforced, and balance, this section we will discuss in our next part. Okay, roll number 8. Are you present, Jason? Enrollment number 8. Are you present? Okay, all of you have got the attendance. Okay, so I am not getting only one student. The remaining one, all of you have got the attendance, so no need to worry and no need to write down in the chat box. So this roll number 8, Jason absent. Then 33, Jodha. Are you present? Jodha Asem. Jodha absent. 35, 36, 37, 38, 39. All are absent. Okay, so then 42. 42 absent. Then I think 43. Are you present? 43. 17. Roll number 17. Jimo. He has just joined today. Enrollment number 17. 17. Jimo. Where is he? 17. I can't see 17. 17. Yeah. Yeah, 17. Okay. So all of you have got that. Okay, so 17. Why you are so late? Nagaito e Jimo? Huh? Enrollment number 17. Why are you so late? We have already finished one chapter. This is our second chapter. Okay, so all of you have got the attendance, so, and our class will end very soon. Okay, so now I am going to share the PDF in your group. Okay, all of you please go through the PDF. Okay, and if you have any doubt in any formula, you can anytime ask me. Okay, you can ask me anytime. I am going to share the PDF in your group. So if anyone have any doubt in that, in any formula, you can ask me. Okay. Okay, thank you.